I think I should have misspoke on something, but anyway, we'll go through this. So if you have chill in F, each of this is a collection of n by n matrices over F with a non-zero determinant. This actually forms a group, and the reason it does is because if you multiply two n by n matrices, then you get a new n by n matrix, right? With entries and and this is the big one. Remember from linear algebra, the determinant of A times B is the determinant of A times B. That guarantees that this is in fact a group length multiplication, right? So well, if F is an infinite field, then this has infinitely many elements in it. But if F is a finite field, suppose it's got Q elements. Then think of it this way. A typical element that I built here has n rows. Everybody agree? Because it's an n by n matrix, right? And each row has, of course, n entries, right? Everybody good? So, how many ways are there to make the first row? Well, because you've got n entries, right? Yeah, Q elements in the field.
You can keep the same.
Row one, you have n entries, right?
Choices.
What's it?
How many choices, Frank?
Q. Right? Because this is a field that has exactly Q elements. There's only one row that you can put in first, right? Because remember, we've got another condition. The determinant has to be non-zero. This is how many choices you have. We'll throw out all zero. I agree. So for row one, I think I get Q to the n minus one choices. Everybody agree? Q to the n, but only one of those choices is all zeros. Everybody agree? But now it gets trickier. How about row two? How many ways are there to build row two? Well, remember, I'm tempted to say Q to the n again. But of course, I could make the zero row, and also now it's easier to make a zero determinant, right? What do I have to avoid to keep from making a zero determinant? What's one way to tell if the matrix has a non-zero determinant? All the rows must be what?
Infinite.
That's correct. So to make this one still be kosher, this one can't be a multiple of this first row, right? And how many multiples of this first row are there? Just take the first row and multiply by all Q elements of the field, right?
Your Q in plus one or Q in minus one.
Yes. So what you're doing is you have complete freedom in the second row, but you just can't have it be a multiple of this one.
Oh,
Because if it was a multiple of this one, then you're in trouble. How about row three? Q squared. Where'd you get Q squared? It's a good guess. Use the force. But now let's tie that all together. Now you pick two rows, agree? Now you gotta make this one linearly independent from those. So you throw out any multiple of this, any multiple of this, and there's Q squared of those. Yes,
We also have to deal with ones where it's dependent on both of them, like a combination.
that's why it's Q squared, right? It goes Q, Q. Any
Right,
multiple,
on either one of them separately, but don't you also have to make sure that it's dependent of their linear combination?
well, that's why it is Q squared. Right, because how many linear combinations do you have of the first two rows? Any Q elements times this, any Q elements times this. All right, so that's Q squared. And now I think it's a little bit easier to see the pattern, right? And so actually, what we get is with the first two rows all the way down. Okay, any questions? Yes,
It's the rows or the columns that.
or it doesn't matter. You can
Doesn't
start from either.
Okay.
Okay. Here's another, this is an important, this is my other examples, matrix groups, there's a lot of different ones. Symmetric groups, there's a lot of different ones. Dihedral groups, there's a lot of different ones, different sizes. This one's important in its own right. This is the quaternion group. In fact, I'm gonna write down all the points. It's this little group for eight. It consists of plus or minus one, plus or minus I, plus or minus J, plus or minus K. And if you're a physicist, you might have encountered this in fact. All the letter symbols plus or minus, all squared to minus one. And we have all relations. I J K, K K, I, K I. Sure, I got that right.
Right, that's our imaginary numbers.
Right. But these stretch out in different dimensions, so yeah.
Those there represent different dimensions beyond like the 2D plane, like one, there's one, there's like.
Right, so
like,
for example, these are
okay.
related, if any of you have ever seen turning. Related to that. Yes.
Is it for field?
Did I do what?
Did we miss it?
Did I?
It's a Q turn.
I missed a Q term, I'm sure did. I need to see that. There we go. Thank you. And finally. These, words. Uh. The first we call the set consists of all words. This is the common terminology made by these symbols. Very verses. For example. If then the free group on S, I'll use that notation, is all the words I can make only with the letter X, right? And its inverse. So elements, this is the set. So for example, I could make a word like this, X. Symbols I'm allowed to use here is any letter, in this case X, and its inverse. This is an example of an element of this. But gosh, what a stupid way to write this, right? What a waste of my time. Anybody abbreviate this for me a little bit? It should be just X cubed, right? Notice these cancel out, right? These cancel out, and once those are canceled, oh, it's worse than that. It's actually it's just a square. Right. Everybody agree with that?
Yep.
That's a free, but it gets complicated fast. For example, for T set X, Y, then the all words made with X, Y, X inverse, Y inverse. So for example, a garden variety element. The word. Now, the free group on these two elements, X and Y, I can make all these words. What happens when I make words with X and Y? What happens if I have two words made with X and Y and I stick them together? What do I get? A longer word with X and Y. So this is closed under multiplication. Is this operation associative? Yes, that's easy to check. The identity is sometimes called the empty word, right? Where you only have the identity there. And how about inverses? How do you build the inverse? Well, whatever word you see, write it reverse and you just invert everything, right? So for example, the inverse of X, Y, X inverse, Y, X. Well, we know that this is X inverse, Y inverse, X, Y inverse, X inverse. Okay. We've got this property earlier. And is this still a word in X and Y? It is.
Yeah, it is.
So this
That's
forms proof.
strange.
Now you can actually collapse these words a little bit. Sometimes if you see things together, this is X squared times X inverse. So this is just X. This is just Y. This is X, Y, X, Y inverse. This is just Y. That's
What,
what's it?
there's a X,
Oh, so you're right.
the X, there's an X, right there
X,
between the Y and three.
Okay. Otherwise, I could have collapsed it further. Doesn't matter. But and I think that's like the lowest that I can get. So that's another way. These are very big groups that you can build. Okay, here's a quick theorem for you guys. I bet you can answer this for me. Just take a guess. So suppose you have a free group on a non-empty set. The free group is abelian if and only if what? So I have a free group on a non-empty set. that free group is abelian, if and only if what? Yes, well, see, when you say the free group, here's what happens, you know, like in the dihedral group. I'm quite about that. Group. In the dihedral group, we had. This is my rotation and this is my flip, right? So we had everything in the dihedral group was words, X and Y, right? We had more restrictions. Because if you ever have n x's in a row, it's the identity, it goes away. This is not a restriction of free group, hence the word free. They're free, there's nothing constraining them. If you have two y's in a row, that's the identity. And there was one more identity. When a y and an x and a y hit each other, it just converted the x.
Yeah.
So this makes it sort of not free. Right? So in the free group with two elements, the word x times y and the word y times x are different. Under what conditions would this ever be available? There's one up on the board to do this.
There's one element.
If you've only got one letter, then it's abelian, and order doesn't matter. If you've got two or more letters, it's not abelian, it's wildly not abelian. Okay, any questions on that? Okay, so that is a beginning zoo of some examples of groups. And now okay, so let me kind of motivate this follows example. Let's suppose that let H equal group generated by A is the A6 is one. So my group H is all words that I can make with A. But if I get six of them in a row, the identity. But now A6 cycles back here, right? Right here. Are these groups the same? No. I mean, the symbols aren't the same. What is the operation that I'm using in the first group? Addition. Everybody agree with that? What's the operation in the second group? It's multiplication, isn't it? Right? I mean, you add the exponents, but what you're doing, like a squared times a cubed is a to the fifth, right? That's multiplication. Agree? But would everybody agree that in some sense, spiritually, philosophically, these two groups are the same thing? Right? I mean, because look, I mean, they sort of correspond. Don't they? The identity here is zero, the identity here is one. Agree? What's the order of one? How many times you got to add one to itself to get zero? It's six. The order of A is six. You got to multiply by itself 6 times. Notice that sort of these numbers here correspond to the exponents in a very natural way. Do I see with that? So, how many groups of order 6 are they? Well, here are two different groups of order 6 that are sort of the same structure, right? What about S3? So I'm gonna use our new cyclic notation. So of course this means the bijection from 1, 2, 3 to itself. It swaps 1 and 2 and leaves 3 alone. This is the function that takes 1 to 2, 2 to 3, and 3 to 1, etc. This is a group of order 6 as well. But spiritually, these two are sort of alike, and this one's different, right? What's one big difference between this group and say this group? Are you able to tell.
S3 is not equal.
That is correct. This one is not a variable. And this one is.
There's also 3 elements of order 2 that's 3.
That's right. This one has 3 elements of order 2 and 2 elements of order 3. This one has an element of order 6, right? So how do we sort through this, right? Because it seems to me like there's these two are different. These two in some kind of spiritual sense are the same. And the way we handle this is with morphisms. These are functions from one to the other that carry information about the group. So let me just give you the definition here. Met G G's. Now, in this beginning, again, I'm going to revert to just concatenation, right, to group operations, but here I want to emphasize it. So here, the operation on G is the circle thing, the operation on H is the star thing. A function B from G to A is called a homomorphism. Homos meaning same, morphism meaning change. So one could construe this as maybe a change of things that are sort of similar. If for all x, y, and g, b of x circle y phi of x circle y, that's the operation in G, is phi of x star phi of y. Because phi of x and phi of y are actually elements of H. This is called a homomorphism of groups. Okay, so let me add to the definition a little bit. Suppose P from G to H is a homomorphism if P is 1 to 1, we say P is a monomorphism. Or sometimes I'll say phi is injective. If phi is onto, we say phi is an epimorphism. Or sometimes surjected or onto. If phi is 1 to 1 and onto, phi is isomorphism. Or sometimes we say a bijection, or actually we should plus say a bijective homomorphism. If phi from G to G is an isomorphism, we say phi is an automorphism. So an automorphism is an isomorphism with the special case that both the domain and the codomain is G. Okay, so some terminology. Let's look at an example or two. Uh. The, here's, um, so the homomorphism, this is sometimes called the trivial homomorphism. This is the homomorphism that takes everything, to the identity. This is always a homomorphism, just assign anything. This is rarely surjective, right? In fact, it's only surjective if H is just itself the identity. B from G to G, given by B, G, G is, it's an isomorphism. This is one-to-one and onto, and in fact, it's an automorphism. Let's look back at this example here. If G is 6 and then B, G to A, given by B, A bar, Z A bar. So just take every element of C6 and associate this exponent over here is an isomorphism. Okay. Anybody remember an isomorphism from calculus? I didn't talk a lot about isomorphisms there. There's very important one. And this will help, I think, demonstrate what I mean about the operation. Remember, to be a homomorphism, we had to have this. I'm gonna write out on the thing. The homomorphism, right, of a rule. Let me give you a couple of groups. Okay, so my first group is positive reals under multiplication. So what happens if you take two positive reals? And when I say positive, I mean really positive, bigger than zero, can't be zero. What happens when I take two positive reals and multiply them together? What do I get? All right, let's see what else. Multiplication associative, you betcha. Well, what about the identity? What is the identity? That's a positive real, isn't it? One is a positive real, so we did go there. And suppose I take a positive real number alpha. What's its multiplicative inverse?
1 over alpha.
Which is positive real, right? So this is a group in good standing. Everybody agree with that?
Yep.
The second group is the group of all reals under addition. Can anybody give an example of a homomorphism from G to H? I saw it without. Natural log. Input, positive real number, output, some real number, can be any, right? Why is this a homomorphism? Well, if we look at phi of x times y, goes the operation in right, the operation in G is multiplication.
One of X, Y, which is all of X, plus all of Y.
That is right. Natural log of x, y is natural log of x plus the natural log of y, which is p of x. So here, the operation turns multiplication. And in fact, this is an isomorphism. Everybody okay with this? And in fact, I'm going to invoke some calculus to do this. To be an isomorphism, it's got to be 1-to-1 and onto, right? What do I know about the natural log?
Well, it's definitely at 1-to-1. It also, this range, ranges from like negative infinity to positive infinity.
That's a crappy drawing of the log right there, but he's supposed to flatten out.
And it's, to me, it's positive reals.
Its derivative is always positive on this domain, so it's increasing. Therefore, it's 1-to-1.
Yeah.
And it's also onto, right? Because the limit as x goes to infinity, the natural log of x is infinity. And it's contiguous, right?
Yep.
So, there you go. By the way, there's an isomorphism from H to G also. Anybody want to guess what that would be?
E of X.
That's right. The exponential is also an isomorphism in the other direction. Right? Any questions? That's why the log works. I'll tell you something else. It's kind of cool. Let me give a kind of a little limit here. This is kind of cool. Let me give you this theorem here, and I'm going to give you an application of this first. Suppose that I have a homomorphism G to H. Right. Let me give you facts here. A, B of the identity of G. You guys had it right. B, B of um, C if the order of X is N and the order of P of X divides it. So if you have an element of group finite order, right, so X to the N is the identity, then the order of its homomorphic image, phi of X over here, must divide that. Yes,
So the cyclic group, no, so the group generated by X has a homomorphism to the group generated by P of X. That's what B implies.
So yeah, if you look at the subgroup generated by X, then yeah, that there's a homomorphism that generated by phi of X, that's correct. B. If B is an isomorphism, then the cardinality in A is the same. Because of course, that would demand that phi is a bijection. E, if B is an isomorphism, then G is built. If and only if H is a B. Okay, I'm not gonna prove all of these because in particular number C, I think I've got it for you on your homework. It's a fun one to prove, but I'm gonna prove at least the first one here. A. Well, for computational purposes, let me just call it something. I know it's something over an H. Phi of one G is equal to H. I want to prove that H is actually the identity of group H, right? Any ideas on how to do this? I feel so dirty doing this. It's almost like I'm doing something naughty. H is phi of one G.
Yeah.
And I don't know much, but I know this. Right, because the identity of G is the identity of G, right? But this is a homomorphism. Right? And this is H times H. So H. Multiply both sides of this by H inverse. So. That little magical piece of sorcery right there. Let me give you some spin-offs. Yes. What is the put here? The identity of this group. Well, a normal one, if you will. What's the identity of this group?
0.
Here's a consequence. Log of 1 is 0. It has to be that way because it's a homomorphism of groups. The identity is 1, the identity here is 0. So the natural log of 1 has to be 0. Looking at the inverse homomorphism, the exponential of 0 has to be because of this. What happens? So those of you that have had linear algebra, what happens when you take a linear transformation and put in the 0 vector? What does any linear transformation do to the 0 vector? It has to go to the 0 vector. That is this theorem here, right? Because a linear transformation, if you look at what you need for a linear transformation, the first thing is, remember how T of V plus W is T of V plus P of W? A linear transformation is a homomorphism of abelian groups. So when you put in the 0 vector, you have to get the 0 vector. This is all kind of fundamental stuff that you probably had to go through and scratch. Gee, I wonder why they made it this way. They didn't make it this way. It had to be this way because these are homomorphisms. Linear transformations are homomorphisms with a little extra scale of multiplication added to it, etc. let me do, I'll just prove number B as well, just because it's fun. I'll let y'all think about the other ones. I've already got that, because I did that part A, right? And this is phi of X inverse X. Right? But this is a homomorphism. So I get phi of X inverse phi of X equals the identity of H, which is also phi of X and phi of X inverse. I took a step there, but I could have put the XX inverse in the other order and got out the other way. So phi of X inverse is the inverse of phi of X. And I'll let you all troll through the rest of it. Okay, any questions on that so far? Okay. So that's a first kind of broad strokes on morphisms. These are the functions between groups that respect the structure. Phi of phi of xy is phi of x times phi of y. It respects the group structure. Morphisms are very important if you want to study, classify, understand groups. And there's another tool by which groups can be studied that's very important. And that is subgroups. When I say the word subgroup, what does that make you? What do you think the definition might be, so to speak? What's a natural thing?
All the elements of the subgroup also belong to the group of Marshall group. So similar to the subspace.
Right. So the group is the parent. The subgroup is a little baby group inside it. Like it's a little. The subgroup is a group in itself that's inside the parent.
You say it's not a subset of the parent group.
Yeah, it's a subset of the parent group that is in itself also a thing. So we'll get back to it. A subset H and G is a subgroup. Yeah, A is also
The same topic.
under the same option. I probably should go. Okay. If I walked up to you on the street, give you a group, I can think of two subgroups for sure. The identity, right? Everybody agree with that? The group G has an identity in there that actually forms a group in a very silly way. What's another one? The entire group. So given the group G itself and identity of G are subgroups. But most groups have a ton more interesting subgroups. So let's see if we can kind of get on a horse and ride, find the subgroups of this. Okay, I'm gonna get the cheap ones. Zero and Z6. That's two of them, because we just said that everything only the identities. Anybody think of another subgroup? Is there another? Or you just
Mop off the ends by one. Like 0 to 4, 0 to 0.
so what's in there?
0 to 4, like 0 to half. But that also.
And everything up to 4?
Yeah.
Well, so you've got one in there, right?
Yeah.
What happens if you've got one and it's a subgroup? You also have to have 1 plus 1. It's gonna be a subgroup. By itself, this isn't a subgroup, right? So once you've got one, you've got to also have 1 plus 1, because it's got to be closed, right? Okay, so if I'm gonna put 1 in there, I've got to put 2 in there. Now what I got to put?
3, 4, and 5.
So I'll get everything in. Huh. Well, that was redundant. And I've learned a lesson here is if I've got a subgroup that's got 1 in it, it's got to be the whole thing. Let me start from that same idea as we have here. Yes, 4. Okay, if you put 2 in here, you gotta have 4. But then that goes back to 0, and 4 plus 4 is 2.
Yeah, that's
This is a subgroup as well. You can check. Like 2 and 4 are inverses. The identity is 0. Right? This is 2. There's also one more.
oh, 0 and 3.
This thing actually has 4 subgroups. Yes,
This might be a silly question, but like, what about one makes it special so that we can't do 1 and 5? What, how do we like?
well, once you have 1 in your subgroup, then you have to have 1 plus 1. And now you gotta have 1 plus 2. Now you got, so once you get 1, you pick up everything. The same will happen if you do only 5.
Okay,
Another way to think about 5 is -1. It's the inverse of 1.
okay.
And so the same thing gonna happen with 5. In fact, what are 1 and 5? What's interesting about 1 and 5?
Same.
These are the only, that's right. These are the only 2 numbers less than 6 that are relatively prime to 6. Okay, and that's why that works. So how many elements are there in V6? There's 6, right? How many elements are in the subgroup? 1, 6, 3, 2. What's true about all these numbers? They divide 6. This is not something we should dismiss as a coincidence. This has subgroups too. See if you can verify these all at once. B, all of this 3. E, 1, 2. E, 1, 3. E. Here. E, 1, 3. So notice in this case, you had 1 and only 1 subgroup for every divisor 6. Here, you've got 1 subgroup for 1, 1 for 6, 1 for 3. There are 3 of them here. So that's something different that happens there. Okay. The next time I will give you, in fact, I'll give you this on the way out. So you can put this in your practice photo because this is actually called the subgroup criterion. This is an important theorem Let P the group. And H and T be not equal to 7. H G is a subgroup. If and only if for all X, Y, and H, X, Y, and X. I'm gonna prove that for you next time. This is called the subgroup criterion, and it will make your life easy on a lot of problems. Okay, any questions? Yes,
Is that X, Y quantity inverse or X, Y?
no, X comes Y inverse. Others? All right, y'all have a good one, and we will see you by Friday.
All right, thank you very